Hey guys, welcome to another video. In this video we're going to be discussing basic pump principles. We're going to be looking at the goal of a pump as well as measurements, specifically pressure and flow rate and the relationship between these two. There's a lot to cover, so let's get going. What is a pump? In this case we're looking at pumps that transfer liquids. We're not going to focus on vapors or gases. Primarily dealing with water, raw water, waste and potable water. Energy, electricity is a significant cost, and we delve into it in quite a bit of detail on how it affects the system. Maintenance is an ongoing requirement and something that we have to take into account in design and during operation and maintenance activities. And capital and operational costs are significant and need to be evaluated at an early stage. So pumps have what we call a best efficiency point, a BEP, and this is a very important principle to understand. Operating too far from this point incurs harsh penalties. Energy per cubic meter rises dramatically, failure happens more frequently, reliability declines drastically, and service delivery becomes an issue. So with the goal in mind that we want to transfer liquids using pumps, we've got a couple of questions to get you thinking. So does a higher flow rate mean that the pump is running more efficiently? And the second question is can you swap one 10 kilowatt pump with another 10 kilowatt pump? The answer for both of these questions is actually no. And the pump's BEP is the critical difference that needs to be evaluated. It is not just flow rate or just power that you can evaluate. You've got to look at all aspects and the pump's best efficiency point to evaluate a like-for-like selection or the correct selection. So if we look at the relationship between flow and pressure, I've tried to simplify it quite significantly. Consider a pump and a vertical pipe extending up into the air. There's a point that exists if you continue to extend the pipe into the air that the pump will not be able to pump higher than that point, and the liquid will get stuck at a certain level. That level we call the pump maximum head or the dead head. Now what happens is at that point you have no flow rate. So on the right hand side we've got a graph, and the graph here has got pressure or head versus flow rate. And in this case, we have no flow rate, so the point is 0, but we have a significant pressure that the pump is experiencing because of that column of water that's pushing back down on it. However, if we have to slowly lower that pipe and the static elevation that it has to overcome slowly decreases to a point where the water starts to, or the liquid starts to slowly trickle out of the pipe. You're then going to have a drop in pressure, a minor drop in pressure, but you're going to have a minor increase in flow rate. And we can show that on the graph on the right. You can see there is now a portion that is considered flow rate, and the pressure drops a little bit. If we have to lower the pipe even further, we can see that this further increases the flow rate. The pressure therefore drops even more, and so forth. And as we move down to the last point, if the pipe had to lie flat on the ground, there's essentially no static head that the pump needs to overcome. It's now pushing out the most flow rate that the pump can possibly push out, and the pressure is rated 0. So on the right hand side we now have a simplified pressure versus flow rate pump curve. And that's just an illustration of how this pump curve is derived. But as I say, this is a very simplified look at a pump curve. So taking a look at this in terms of a summarized graph, we've got A, B, C, D, and E, and as we've lowered that pipe and that vertical static head, we've increased the flow rate, but we've lowered the pressure that the pump is experiencing. So there is a very definitive relationship between the flow rate and the pressure. Operating at point B and what the pump is experiencing compared to point E, the pump experiences very different attributes. And it's still the same pump. And that is a very key principle to understand. So what exactly is pressure? Pressure is defined as the force that is exerted on a unit of area. P is equal to F over A, force over area. If we apply a pressure to a surface of a liquid, the pressure is transmitted uniformly in all directions across the surface, even the walls and the bottom of the vessels containing the liquid. And this is important to understand that gases and air are compressible. However, liquid is not. Liquid therefore transmits forces in all directions. So, perhaps you've heard the term head before. What exactly is head? And this is a term that is used with regards to pumps and pump systems. Pump head is the vertical distance in meters that you can pump the liquid. So in the image on the right, it's defined as C. For instance, if your pump is rated for a maximum head, in this case 10 meters, this does not mean that you're restricted to a 10-meter long pipe in a vertical direction, as you could also use a 50-meter long pipe, provided the final discharge point is not higher than the 10-meter static elevation above the liquid being pumped. So how do we know if the pressure gauge readings are good or if they are bad? If you walk into a station, do you think an engineer will know the difference between a reading that is good or bad, or is there more information that is required and something that is site specific? The only way to find this out is you have to go back to the original manufacturer and they'll tell you if it is good or if the readings you're getting are bad. The difference is all manufacturers' data are in meters and not in kilopascals bar or MPa that you normally read off a pressure gauge. And let's just delve into why this is. So the relationship between pump head and pump pressure can be illustrated with a simple formula. The conversion between kPa and meters is H is equal to P over G times Sg. In this case, head is equal to pressure over gravitational acceleration times specific gravity. Gravitational acceleration and specific gravity are both constants, with specific gravity relating to the density of water, and we round this off to 1 gram per centimeter cubed, while gravitational acceleration is 9.81 meters per second squared, which is normally rounded off to 10 meters a second squared, just allowing for easier calculations. Without delving into the nitty-gritty of the formula and the units, we can see that head is now equal to pressure in kPa divided by 10. So to better explain head, let's take a look at an example. So using the example on the right, we've got a suction level in a sump, and it's indicated as level A. And then we've got level B, which is indicated as the pump discharge. In this case, there is flow rate coming out, and it is below the deadhead or the maximum elevation height that the pump is capable of pumping. And then we've indicated C as well, which is the pump deadhead or the maximum head that the pump is capable of achieving. So a reading on a pressure gauge at the bottom of the tube, let's say it was a plus or minus 100 kilopascal reading. In this case, we knock off a 0 on the end, and this means that there is a 10-meter column of water that the pump is experiencing in the clear tube. So there's basically a 10-meter discharge pressure. So leaving the suction side for a moment, we can have a look at the manufacturer's published information and see if the pump is happy with this or not. Now let's have a look at TDH, or the total dynamic head. To work out what the pump sees, which we refer to as the total dynamic head of the system, we need to find out what is going on the suction side of the pump or in the sump. In this example, we clearly see that the discharge point will always remain at the same distance, length, and height above the pump. It won't change with time or due to levels, as the pipe discharges into the top of a reservoir or tank, and it is not affected by the conditions within the tank. We do, however, notice that the suction sump level can change depending on whether the sump is empty or full, and this can greatly increase the amount of work that the pump needs to perform in order to lift the volume of liquid, and this is dependent on the total dynamic head that the pump experiences. If the system is existing and in operation, the total dynamic head the pump sees can easily be calculated from the discharge and the suction pressure gauges. This is done by taking the discharge pressure reading minus the suction pressure reading, which in essence will give you the amount of head or pressure that the pump has been able to contribute, therefore the TDH that it is experiencing. For this system, if we had to calculate what the total dynamic head was, we would need to add the static head in meters as well as the friction head in meters caused by the fluid flow in the pipes. This would be looking at the length of the pipework as well as the number of bends and valves, etc. And then we'd also need to take the velocity head into account, which is a function of the speed at which the liquid travels. Now that we know what pressure and head are, we can have a look at the flow rate. If we can find out what the flow rate is, combine this with the total dynamic head, and we will get a good idea of the state of the health of the pump. Flow rate is the volume of liquid that is able to pass within a unit of time. The flow rate depends on the area of the pipe or channel that the liquid is moving through and the velocity of the liquid. This is measured in cubic meters per second or liters per second. Flow rate is represented by Q, and the formula is Q is equal to area times velocity. In an existing system, this can be read from a flow meter such as a mag flow meter or a DP flow meter, or if there's no existing fixed flow meter, then a clamp-on ultrasonic flow meter can be used to check the flow rates. The picture on the right shows a permanent ultrasonic clamp-on flow meter. If the concepts we have touched on are relatively new to you, or you feel like you need to go over them again, then please feel free to re-watch this video as many times as necessary. We will be going into much more detail in the coming videos on these principles, and things will become a lot clearer towards the end of the course when all the pieces come together. To run through another example before we end off this unit, let's have a look at the system below. We will notice that the suction conditions of this example are different, as the suction level of the liquid is well above the inlet to the pump. This is referred to as flooded suction and greatly improves the pump's ability to perform as designed. The positive suction head adds energy to the system and reduces the amount of work that the pump needs to do. This means that the total dynamic head in this example is less than the previous example when the suction level was in the sump under the pump inlet level. The total static head in this example is therefore the discharge static head minus the positive suction head. Let's summarize the learning points of this video. At a no-flow condition, the pump is still using energy but not delivering any volume. At an intermediary height, we got some flow and there would only be a small increase in the power consumed. At the lowest level or height, there was plenty of flow rate, but the pressure was significantly reduced. So TDH varies with flow rate. TDH can be determined with the suction and discharge pressure gauges, and pumps work best when the TDH and the flow rate are balanced. The information published by the pump manufacturer will tell us what the pump's head versus flow rate balance should be. Thanks for joining. We trust that this video on basic pump principles has helped you better understand pump systems.